So the limit of a function, if you had to explain a limit to maybe like somebody in algebra, even after just one day, I kind of wondered what you would say. If you had to explain limit to somebody that was absent yesterday, what would you say? Why don't you just have a little conversation with your neighbor, what do you think when you think of a limit of a function?
I know what it is, but I could not explain.
Terrible.
You would fail somewhere.
So what did your neighbor say? What did your neighbor say, or what did you say? What'd your neighbors say back there, Nate? Because you had a chatty neighbor.
She said, it's like as x approaches a certain coordinate, it's where the graph is intended.
Okay, good. It's where the graph is intended to be. Is he a good listener? What else did your neighbor say, Jake? What did your neighbor say? Who are you?
He said it's the intended y value as x approaches the value c.
Good. So it's a y value. To kind of add to that, it's a y value. Do you have to get to the y value? You have to actually reach that y value. Not necessarily, right? You just have to have intended to get there, which implies that there might be a hole in the graph. And there might be some other things that we'll keep talking about today, but a limit doesn't necessarily have to be where you go, it's just where you intended to go. Now, we did, I think, 4 problems, and kind of purposely I did them all a little bit different. I don't want to say much, because I want to just say, did you use something that you saw yesterday, and see if you can find these limits? Is this something new? Well, it's new problems, but I'm wondering if you can use something from yesterday to kind of find those limits. Go ahead. It's another thing to kind of, if you want to talk about, or you just kind of want to start doing something, you're going to look back at yesterday probably.
You said like, it doesn't have to be now, I just wondering.
You also won't have to necessarily do it now, but
Yeah.
I'm going to give it to you so that probably sometime during the period you can. I know some of you might be saying, well, I wish we could do a few more problems. We will. But I like using this style to let you guys explore and maybe find out that you're right, or find out that you just need to adjust something. Did you realize that there were at least 2 different methods shown yesterday? If you don't realize that there's 2 different methods, that's fine. But try to use some method that is coming to mind. But there's actually 2 ways that you could go about these. I see more than a few of you operating a calculator. That is not a bad thing at all. That is one of the methods that we did yesterday. We looked at the graph. So again, that is not a bad method at all. Because intended heights can be determined by looking at y values. I'm not gonna put someone on the spot on this one, but I do wonder, anybody, what do you think? How did you use? Where were you looking to use the graph for the first limit? Anything that you would like to put into that discussion? Where did you look? How did you use the graph for this first one? Can we go to x equals 3? Okay. The answer actually is yes, we can. If this was like an algebra class and the teacher said, what's going on in x equals 3? Well, you could go there and you could see that what's going on is that you happen to have an x-intercept. I say happen to have an x-intercept. I don't want you to think that the x-intercept is significant, but I do want you to realize that the y value right there is significant. So I can go to x equals 3. Now, just a little side note, if your eyes were like going somewhere else, you're not alone, because there's other stuff going on, like over here. But the truth is, none of that matters. The only thing that matters is what's happening right here and right here. Basically, these yellow arrows insinuate that I'm approaching x equals 3. And so it looks like the intended height, the actual height is 0. Okay? Now, it doesn't matter that it's the actual height, but it does matter that it's intending, and that y value is, again, 0. Now, on one level, that's all there is to that problem. But on another level, we can find that answer another way. Was there anyone that wasn't using a calculator, like in the nature of graphing it? Or now that I mention it? Now, we call that like a substitution method, I mean, kind of basic math, but if you plug in what you get 0/6. Now, it is meant to make us pause and ask ourselves, can you do 0/6? Sure. You can do it last year, this year, and next year. 0 divided by 6 will always be 0. Okay, and basically it gives you a confirmation that that's the y value. Okay, so the limit as x approaches 3 is 0. Now, did you notice that it's the same function, but it's a different limit? It's the same function, but it's a different limit. And I kind of ask you the same thing. Can we go to x equals -3? Maybe that has like a different answer. Can we go to x equals -3? Let's think of it more like this. Can we approach x equals -3? Now, if I approach x equals -3 on this side, then I'm sort of sliding down this slippery slope. Where am I sliding down to? Where am I sliding down to? Well, we could say to -infinity. It's kind of a strange answer, but it's true that it keeps going forever. What if I approach -3 from this side? Well, if I approach from this side, then I'm trying to climb up this crazy warp wall, and where would I go? You could also say you don't go anywhere because you never get there. But what you want to ask yourself is, what intended height am I approaching? Okay, what intended height is that you are approaching no height? Okay, because infinity is not a height, it's not a number, it's not a value. -infinity is not a height, it's not a number, it's not a value. And if you didn't see this yesterday, but today we want to say that this limit does not exist. this limit does not exist. Now, the reason it does not exist, kind of like yesterday where maybe you want to write extra stuff in your notes, is because there is no intended height. And as I suggested, infinity is not a height. Infinity is not a number. So there's no intended height. You can always add that if you need to your notes. What about this substitution idea? You know, kind of like just plugging in -3. It's worth investigating. Now, yesterday you saw 0 over 0. Now, today we have like 6 or -6 over 0. And you're correct, you can't do that. But I want to kind of add something to that. I want to add that it insinuates something. It insinuates that you have a vertical asymptote. Now, what I'm suggesting here is that when you have a 0 in the denominator, that's always going to be a vertical asymptote, which also insinuates that the limit does not exist. Think about it, kids. You've heard of vertical asymptotes, okay? It's not like a new idea, but today, think about the height that you approach on a vertical asymptote. Okay? And you should be thinking, yeah, no height. You don't approach a height, again, on a vertical asymptote. Now, here's something that you might want to put in a little box, and it's something that we said just now, and we're going to keep saying, so it's helpful to show it to you. It's the use of the number 0. When 0 is in the numerator, not to overthink this, but when 0 is in the numerator, that's always been equal to 0. You know, that's kind of what happened in the first problem. Again, when 0 is in the numerator, not to overthink it, because that's always been equal to 0. When 0 is in the denominator, we want to remember that that's a vertical asymptote. When 0 is in the denominator, that's a vertical asymptote. Okay, and so new for calculus is that means the limit does not exist. Kind of surprised when I said limit does not exist that there wasn't maybe like a little rustling or smiling. I can't see your face, maybe that's why, but have you heard that limit does not exist before? So I don't know if you're I don't advocate the movie. I'm not sure if the movie advocates good things, but it does have good math in it. I'll show you the video clip a little later, because we need to kind of appreciate it a little more. If you don't know what I'm talking about, I think Emily does. What movie is it?
Mean Girls.
Yeah, so anyway, I'll show you the clip, but we'll talk a little more about limit does not exist to get an appreciation of that. Now, one more. This is new. It was said yesterday, but you're gonna realize like, oh, this is important. That's why I put in this little list. This is the one that usually still gives kids the most trouble, but you gotta kind of understand that 0 over 0 does not determine anything. It's called indeterminate. That's a fancy word for does not determine anything. In other words, try something else. Now, I hope you don't do this, but I mean, kids have done it in the past. They'll sitting down, taking a test, trying to show knowledge. They get 0 over 0 and say no solution, or say limit does not exist. Or maybe they say 1 or 0. Okay, none of those things are true. The only thing that's true about 0 over 0 is I don't know what the answer is. It means turn around and do something else. yesterday, maybe you remember that we got 0 over 0. We turned around and factored the problem, and out popped the limit, -2. Okay, so 0 over 0 is an indeterminate. More to come with that. If you're able to look at your book, I want you to look on page 57. Page 57. Properties of limits. Properties of limits. And we might flip over to page 58 also. We might flip over to page 58. Take a look at page 57 if you're able to do that at the bottom. Now, I'll share with you here that I don't think that you're gonna need to write these things down, but I do think that you need to hear them so you understand, oh, okay, I'm allowed to do this. So if a property of a limit states what we're able to do. Look at the first one. It says that the limit as x approaches c of k equals k. Okay, now I want you to be able to read a math book and understand what it's telling you. If you look at the little print beside it, it says that the limit of a function that is constant. Now stop right there. A function that is constant would be a function that equals a number. I want you to picture with me a graph of a number. What's the graph of a number always going to look like? It's always going to be what kind of straight line?
Horizontal.
Horizontal. What's the intended height of a horizontal line? Okay. You have your answer. That's why it's always equal to k. Okay, so the limit of a number is a number. You can write it down if you want to. I'm not telling you not to, but it might be something that if you just think about it, you're like, oh, of course. Now, how about the limit of like x approaching c of x? In other words, the limit of x. X is a function, okay? It's, by the way, a diagonal line. But more generically, it's a function that you can plug into. Just like we did with these problems. If you have a function that has x, then you can plug in for x. Okay, and that's all this is really telling you. Geez, if you plug in c, well, you're going to get the limit. Now it happens to equal c, because that's what happens when you plug into a little function like x. Okay, but you can also plug into any function with x. Now those two properties, I don't want to call them common sense. I hope that you hear me out that I think they're more like calculus common sense. If you just think about it, that's what the intended height would have to be. Now there's some other properties on the next page, 58, which might fit into that calculus common sense category. Meaning if you just think about it, you will be able to use these properties without like feeling like you have to copy them all down. Look at that yellow box. Property number 1, it says that the sum of a limit of f of x plus g of x. Now that would be like having two functions, f of x and then another function g of x, and you're adding them together. Well look, the limit is going to just be the sum of the limits. In other words, L plus M. Okay, all this is really saying is that you can separately find each limit and then add them. Just like you would always do with an addition problem. Same thing with subtraction, it's property number 2. I can subtract L minus M. Okay, now it's the same thing with multiplication, and quite frankly, all the way down. And what you're going to find out here is that this is kind of like applying algebra to a limit problem. Okay, now I say kind of, that's because we have to have permission to do it, and that's what those properties let us do. I know, most math show me, right? So I'm going to show you, but you're going to say, hopefully, in the next 60 seconds or so, that this kind of used calculus common sense. We might need like 90 seconds, but seriously, what we have here is the limit of x squared plus 2x minus 6. Now, according to those properties, and this will be the only time you see me do this, because honestly, it's extra work and it's not necessary, but I still want to show you one time. According to those properties, I can separately do the limit of x squared, separately do the limit of 2x, separately do the limit of 6. And I do want you to see that, because that's what all those properties were insinuating, that I can like split up, I can separately do each of these limits. And the good news is that it's kind of easy to do each of these limits, because from the previous page, you can plug in. You can plug in, so yeah, you're gonna plug in 4, you're gonna square it, yeah, you're gonna get 16. You're gonna plug in 4, you're gonna multiply it by 2. Now this gives us an opportunity to realize what this is saying, the limit of 6, the intended height of 6. Well, it's always 6. Now, when all the dust settles, all I really did was just plug in. And I could have did that back in the beginning, which is what you're gonna do. Okay, so, but technically you're allowed to do that. Technically you're allowed to split up and find each of these limits. Now you'll get that problem right. Next time you'll get it right, hopefully 9 out of 10 times, unless we make a little simple arithmetic mistake. But what I want you to realize is what you really did. And what you really did is you found something along this parabola. Okay, now the parabola I'm referring to is the entire function. And the something that I found was the intended height. The intended height. Okay, that intended height was 18. In fact, the actual value was 18. Okay, but each of these problems always goes back to that original definition from yesterday. Okay, so intending to get to the number 18, to the height of 18, as I approach 4. Okay, some of that's extra. Okay, if you're like, do I have to do all that? Like I said, no. Okay, but I want you to realize what you're getting here. Now there's another kind of problem that sort of circles around these properties, and we're gonna move on to something else. But this should be good here before lunch, or at least we'll get started. It's a little different problem where you're told some stuff. So let me write a few things down before you make too many conclusions. You're told that the limit as x approaches 2 of f of x is 5. And don't read into that too much. It just means there's some make-believe function. There's some make-believe function that as I approach 2, the intended height is 5. Let's say you're also told that the limit as x approaches 2 of g of x is -4. And are you kind of getting a little bit of my drift here? I'm just giving you some limit statements about some make-believe function. Now, it makes for a pretty easy math problem, because now you can find the limit of a new function, like 3f of x divided by g of x. So find the limit of 3f of x divided by g of x, which is kind of like a new function that uses f of g. And again, we end up with what you will say is a pretty easy problem, because you're just going to substitute. But you're allowed to do that because those properties say so. The property says that I can individually do the limit of 3. The limit of 3 is 3. I can individually do the limit of f, 5. And individually the limit of g is -4. Of course, to a good math student, you look at that and say, well, you just kind of substituted those numbers. Right. Okay, but the properties say that we can do that. Okay, now there's nothing to graph because we don't know what the function actually looks like. But if we did have a graph, we would just see that the height was getting close to -15 fourths as I got close to x equals